Hello. Today we are going to look in more detail at finding the area underneath a curve using integration. So this builds on the work that we would have done on definite integrals, and it also links into an area and volume type question in terms of the trapezoidal rule. So this argument is somewhat similar to the trapezoidal rule of finding the approximate area underneath curves. Now, we have our blue line function here. It looks a little bit like a positive cubic, but that doesn't really matter for our purposes. And we want to find the approximate area underneath it. So we don't have a formula for the area of this shape. So what we can do is break it up into shapes we do have formulas for, and the easiest one is rectangles. Trapezoidal rule uses trapezoids. The easiest version would be rectangular. Little chunks, and we can add up the area of these little delta areas, these little sections of the area. When we add all of them up, we should get an approximate value for the area between the curve and the x-axis. Now, the area of any one of these little bars is going to be delta x, the width of them, the change in the x, by whatever the y function is. Whatever the height of our bar is will be the height of our function at that point, approximately. Now, to get the area of a single bar, your delta area would be equal to the height of your function at that value of x times the width of your bar. Now, this is all quite approximate. This isn't a full derivation or anything. It's to give you a feel for what's going on. If we wanted to get the approximate area underneath the curve, instead of just a single bar, we could add up the area of each of these bars, and we would get the approximate area underneath the curve. So the approximate area, this squiggly bracket means approximate area, would be equal to the sum of all of the individual areas of the bars. So far, hopefully so good. Now, at the very beginning of integration, we said that the integral symbol looked like an S. And the reason it looked like an S was because it meant a sum of things. So this is our normal symbol for a sum. If we make our delta x's infinitely small, if we shrink the size of our delta x's down to make them infinitesimally small, then we'd be adding up an infinite number of really, really thin bars. And our approximation would get really, really good. If we look at where the error is in the curve, in the area under the curve, you can see a gap here, a gap in here, because our bars are so wide that we're missing bits of the area that we should be picking up. But the narrower we make these bars, the narrower we make delta x, the more accurate our area becomes. And if we make them infinitesimally small, if we effectively let them go to 0 in size, but in the limit they would go to 0, so this is another instance of using limits. In the limit as delta x goes to 0, we end up, instead of getting a sum, we say we get an integral. So this is where the fact that our integral symbol looks like an S comes from. It is the infinite sum of a bunch of little bits of area to give us the complete area underneath a curve between A and B. So this isn't a formal derivation. You can do a formal derivation, but we aren't required to. So this is just to give you a feel for why this is working. That's all. And to highlight again that this is an idea closely connected to the trapezoidal rule. And there have been exam questions that link those two things together. One final note before we get into a question is that the area between a curve and the y-axis, so here I got the area between the curve and the x-axis, the area between a curve and the y-axis would be exactly what we might expect it. The area between the curve and the x-axis is integral from a to b of y dx. The integral for the y-axis would be the integral from a to b of x dy. So get x in terms of y and then get the derivative with respect to y instead of getting the derivative with respect to x. So here we have a little sketch. If we had a curve like this would be like a quadratic in y instead of a quadratic in x, and we'd be integrating from a to b, and that would give us the area in between the y-axis and the curve. exactly the same concept. The letters just look a little bit different, but all of your intuitions still work. Now, let's have a look at the area of a specific example. So if we want to know the area between the x-axis and the function from 0 to 2 pi of sine x, very simple integral to start off with. Now, immediately we might have a suspicion as to what's going to happen if we look at our sketch. So we have area above the x-axis and we have area beneath the x-axis, and we know our area comes from multiplying the y value of our function by little delta x. So what might happen to the area of the function underneath the line? Well, we're going to play this through and see what happens. So if we get the integral, if we forget about our intuition of our function for a moment and just try and play this through, let's see what happens. If we get the integral of this, the area would be equal to minus cos of x from 0 to 2 pi. That would be equal to minus cos of 2 pi minus cos of 0 be equal to minus cos of 2 pi would be 1 minus cos of 0 is 1, so minus 1 would be equal to minus 1 plus 1 would be equal to 0. So we get something that's an obviously absurd answer. We can see there is an area between the function and the x-axis, our blue shaded in area here. There should be no reason why we would be getting an area of 0. There's clearly an area between the curve and the x-axis. But we can probably see what's going on. This area here is going to be negative, and this area here is going to be positive. So we get a positive area up here and a negative area down here. And it so happens, because of the way that the sine function works and that I chose a full rotation, they exactly cancel each other out. This area sums to 0 with this area. And that's what we've got going on. So when we get integrals of the function against the axis, we have to be very careful. Effectively, whenever we're doing integration of areas, we need to be very careful that we aren't missing out on where areas could be positive or negative. So a core thing we have to look out for with getting the area using integrals is, where is the function above the x-axis, where is the function below the x-axis, and we're going to get the integral of this section here and then the integral of this section here separately, and we're going to turn the negative one positive so that we can add up the total area that we are talking about. So we need to know where our break between our positive area and our negative area happens. Where is this going to be? Well, we know that the sine function is symmetric, so we know that that's going to happen at, or it's symmetric over its period, so it is going to be happening at pi. But in general, you would be looking for where the sine function is going to be equal to 0. So where is sine of x going to equal 0? Well, we have to go to our unit circle for that. We know that our y output in our unit circle is going to give us our sine function. That unit circle is just a little bit small to be very useful. So where is our sine function, our y output, going to be 0? Well, when our angle is 0, so when our angle is 0, we would have y would be 0. When we rotate round through 180 degrees or pi radians, we're working in radians effectively here, we'd be at y is 0. And when we rotate all the way around 360 degrees or 2 pi radians, we would get y is 0 again. So that tells us we have our roots effectively of our function going on at angle is 0, angle is pi, and angle is 2 pi. So our unit circle helps guide us as to where we need to go. So that is another way of working out what angle you need to do. But in general, find out what the roots of the function are. So now we know that we need to break this integral up into 2 parts. We're going to get the integral from 0 to pi. That's going to give us the positive area, plus the integral from pi to 2 pi. Now we know from the graph that this is going to end up being negative, so we're going to have to take the positive version of this. So you can put absolute value signs around it if you like to remind yourself, but we're going to take the positive value of this integral. Another thing to be wary of is these can get quite long, so make sure you leave yourself a good width on the page to write these out. We're going to have sine goes to minus cosine of x from 0 to pi, the integral of both. Sorry, pi to 2 pi. So I've broken up my positive and negative parts, and now I'm going to integrate them separately and add up my positive answers. Minus cos of 0 plus minus cos of 2 pi. The larger number always goes first. Minus cos of pi. So we get cos of pi is minus 1. Minus cos of 0 is 1. Cos of 2 pi is 1. Minus cos of pi is minus 1. It's a little bit messy, but so long as we do each step little bit by bit, we won't run into any serious problems. So we end up with 1 plus 1 plus minus 1 minus 1 equals 2 plus minus 2. This bit we are just going to take the positive value, so if you like you can take the modulus of it. This is why we needed to do this in 2 steps, because we were having plus 2 minus 2 summing to 0. This is why we were ending up with an area of 0 erroneously to begin with. So we end up with 2 plus 2 is equal to 4. So this is our key little step that we need to keep in mind for any type of function we're getting the area of. We need to make sure that we have the parts where we're above the x-axis and below the x-axis sorted out, and that generally involves finding the roots of whatever function we are dealing with. In this case, we had to figure out the trig roots in the range, and often you'll just be solving some polynomial type things like x squared or x cubed in order to find the roots of the function to figure out your intervals for integration. And that's the first part of what we need for the area involving integration.